You've probably heard stories of strange lights flickering in the sky just before a major earthquake hits. Some call them earthquake lights, and for decades, they've been a source of intrigue and mystery in the scientific community. Are they real? And if so, what are they? More importantly, could they be an early warning sign for a massive disaster? First, let's take a look at the science behind these strange phenomena. Earthquake lights, or EQLs as they are sometimes called, are flashes of light that appear in the sky before or during seismic events. They can range from a faint glow to brilliant, multicolored beams that dance across the horizon. While these lights have been reported throughout history, they've only started to capture serious attention from scientists in the last century. One of the most notable recorded incidents of earthquake lights occurred just before the 1906 San Francisco earthquake, which measured a devastating 7.9 on the Richter scale. Eyewitnesses reported seeing strange lights in the sky. Some described them as blue or white flames, while others saw balls of light hanging over the city like eerie orbs. These reports didn't just come from casual observers. Several credible individuals, including scientists and firefighters, confirmed witnessing the strange phenomenon. But before we get too far ahead of ourselves, let's take a closer look at how an earthquake could cause such bizarre lights to appear in the sky. Scientists have proposed several theories, though none of them have been conclusively proven. The most widely accepted explanation involves the release of energy from the Earth's crust. As tectonic plates shift and grind against each other, they generate a lot of stress and friction, which can cause the minerals in the rocks to release electric charges. These charges could then ionize the air, creating visible light. Some researchers believe that these lights are the result of piezoelectricity. Piezoelectric materials, like quartz, can produce electric charges when they're compressed or deformed. Since the Earth's crust contains large quantities of quartz, especially near fault lines, it's possible that the tectonic activity involved in an earthquake could be enough to trigger a piezoelectric effect, causing bursts of light to appear in the sky. This theory is still speculative, but it fits the data in many ways. Yet, there's more to the mystery than just electricity. Some reports describe lights that appear to have unusual properties, behaving erratically or seemingly defying the laws of physics. For instance, in 2009, residents of the Italian town of L'Aquila witnessed strange violet-blue flashes in the sky just days before a powerful earthquake struck the region. The lights were visible for hours, but no one could explain why they appeared so long before the quake, leaving many to speculate whether these lights could act as a warning system, pointing to something more mysterious at play. Another theory involves the ionization of the atmosphere. When an earthquake occurs, it creates a significant amount of energy, and it could cause a disturbance in the Earth's magnetic field. This disturbance might affect the ionosphere, the layer of the Earth's atmosphere that contains charged particles. In areas where tectonic plates are active, the shifting ground could lead to an increase in the amount of charged particles in the air. These charged particles can then create visible light phenomena, such as halos or flashes, much like what happens during a thunderstorm. Again, this is an area of active research, and while some scientists believe this could explain earthquake lights, the exact connection is still unclear. But these lights are not just limited to earthquakes. They've also been linked to other seismic events, such as volcanic eruptions and even nuclear testing. This has led some to question whether earthquake lights could be a universal signal for any major disturbance in the Earth's crust. Interestingly, there have been reports of these lights appearing before events that didn't involve earthquakes at all. For example, in 2010, a massive landslide in China caused thousands of tons of earth to move, and just before it happened, strange lights were observed flashing across the sky. Could it be that this phenomenon isn't limited to earthquakes? Are there other types of geophysical activity that could trigger these lights? To understand this further, let's look at a more modern example, the 2011 earthquake in Japan. Just before the massive 9.0 earthquake struck, reports of strange lights began surfacing in the region. Witnesses claimed to have seen bright flashes and glowing streaks in the sky that lasted for several seconds. This wasn't the first time strange lights had been seen in Japan. Similar phenomena were observed before the 2004 earthquake in Sumatra, which was also catastrophic. While it's still unclear if the lights were connected to the seismic event, they have led some scientists to look for patterns that might suggest an underlying cause. If these lights are indeed a precursor to major seismic activity, they could provide a valuable tool for predicting earthquakes in the future. Imagine if scientists could develop a method to detect these lights early on, giving communities a warning system that might save countless lives. However, there are some significant challenges in making this prediction a reality. For one, earthquake lights are still relatively rare, and their appearance is often inconsistent. Not every major earthquake is preceded by these mysterious flashes, and sometimes, they appear for seemingly no reason at all. There's also the problem of timing. In many cases, the lights appear hours or even days before an earthquake strikes. This makes it difficult to act on them in time. Imagine seeing bright lights in the sky and knowing that a massive earthquake could hit, but not knowing when exactly it will happen. This level of uncertainty is one of the main reasons why earthquake lights are not yet considered reliable indicators for earthquake prediction. Nevertheless, scientists continue to investigate earthquake lights, and some are beginning to suggest that there might be more to these phenomena than we've realized. In the coming years, advancements in technology and our understanding of geophysical processes might shed new light, pun intended, on these strange occurrences, and potentially, they could even help us unlock the mysteries of earthquake prediction. What we do know for sure is that strange lights in the sky before a massive earthquake are no mere coincidence. While we can't yet explain exactly why they happen, the connection between these lights and seismic activity is too compelling to ignore. As research continues, we may one day uncover the secrets behind earthquake lights, and perhaps even develop a way to predict earthquakes with greater accuracy. A possible reason that scientists have been investigating regarding the strange lights appearing before earthquakes lies in the phenomenon known as seismoluminescence, a term that sounds just as peculiar as the lights themselves. Seismoluminescence refers to the light emitted from the ground during seismic activity. While the exact mechanism is still being studied, one theory proposes that when tectonic plates grind against one another, the immense pressure builds up in the Earth's crust, and in some cases, this pressure can result in the emission of light. This happens when certain minerals within the Earth's crust, like quartz, are subjected to intense stress and experience a phenomenon known as triboluminescence, the emission of light caused by mechanical stress on certain materials. In the case of earthquakes, when the tectonic plates shift, minerals deep within the Earth's layers could be compressed, creating enough energy to cause a brief, localized flash of light. These flashes could, theoretically, escape from cracks and fissures, making their way through the surface to be visible in the sky. This might explain the strange lights seen before a quake. There are documented reports of lights similar to these occurring in areas where major seismic events later followed. In Japan, for example, there have been reports of earthquake lights that have appeared in the sky just before major tremors hit. While it's not always certain, many researchers think there's a possibility that these lights are tied to pressure-induced changes in the mineral structure below the Earth's surface, causing an energy release in the form of light. One of the most well-known instances of this phenomenon was the 2000 earthquake in the Indian Ocean, which was followed by reports of unusual flashes of light in the sky in the days leading up to the disaster. Similar phenomena have been observed before the 2011 Tohoku earthquake in Japan, leading some to wonder if these lights could be more than just a coincidence. In fact, the lights may not always be visible to the naked eye. They could be faint and only picked up by sensitive equipment, or perhaps noticed by people who are looking up in the right place at the right time. But there's more to it than just pressure on the Earth's minerals. Some experts suggest that the lights could be a result of the electrical charge building up in the atmosphere itself. When large-scale tectonic shifts occur, the stress and movement within the Earth's crust might create an electrical imbalance. This, in turn, could cause atmospheric ionization or static charges to build up. Under the right conditions, these charged particles could ionize the air and lead to glowing phenomena in the sky, lightning-like displays before the earthquake even occurs. This idea ties into something called the piezoelectric effect, where certain materials, under stress, generate electrical charges. If the ground shifts in just the right way, it could release enough energy to create visible flashes of light. On top of that, there's the possibility that these lights are related to the seismic activity affecting the magnetic fields of the Earth itself. The crust of the Earth is full of electrically conductive materials. When an earthquake happens, it might cause a disruption in the natural magnetic field of the planet. This change in the magnetic field could, in turn, affect the ionosphere, where charged particles interact with the Earth's magnetic forces. Some researchers believe this could create aurora-like phenomena in the sky, similar to the lights seen near the poles, though the cause would be a completely different interaction between the Earth's magnetic forces and seismic disturbances. But while this theory is fascinating, the scientific community still remains cautious. The correlation between strange lights and earthquakes is still considered speculative because there hasn't been a concrete, reproducible experiment that definitively links the two. Many of these occurrences could be the result of atmospheric conditions, electrical phenomena, or even human-made sources like nearby power lines or flares. Yet, the presence of these lights is undeniably unsettling, particularly when they appear just before devastating quakes. It's as if the Earth is trying to warn us, signaling the impending danger with an eerie glow in the sky. Interestingly, some regions have become hot spots for these mysterious lights, which is why researchers are especially keen on monitoring the skies in these areas. The region around the Pacific Ring of Fire, home to many of the world's most active fault lines, has been a site for numerous recorded instances of these strange lights. The frequency of seismic activity in this region could explain why lights are more commonly observed in such areas. Earthquake-prone zones, such as California, Japan, and Chile, have reported some of the most striking observations. These areas have also experienced some of the largest and most catastrophic earthquakes in recorded history, lending weight to the theory that there could be something significant to these lights. To further explore the potential connection between strange lights and seismic activity, researchers have been delving into the role of electromagnetic radiation as a potential precursor to earthquakes. One of the lesser-known but intriguing aspects of seismic phenomena is the electromagnetic emissions that can be generated by tectonic stress. Earth's crust is composed of various materials, many of which are piezoelectric, meaning they generate an electrical charge when subjected to mechanical stress. When two tectonic plates move against each other, they don't just create seismic waves, they also cause microscopic electrical discharges in the rocks themselves. These discharges can potentially escape into the atmosphere, manifesting as electromagnetic radiation. This radiation could then interact with the ionosphere, a layer of the Earth's atmosphere charged with ions and free electrons. The ionosphere is known to play a crucial role in the Earth's electrical balance, and any disturbance caused by electromagnetic radiation could potentially create visible effects, such as the glowing lights that have been observed. Some researchers hypothesize that these electromagnetic discharges might influence the ionospheric conditions in such a way that they lead to the formation of luminous phenomena, similar to what we see in the auroras near the poles. In these cases, however, the energy isn't coming from the sun, it's being generated by seismic activity beneath our feet. A major challenge in understanding these phenomena lies in their unpredictability. Electromagnetic emissions from tectonic activity can vary greatly depending on the type of fault, the composition of the rocks, and even the depth of the seismic event. The complexity of the forces at work means that even if there are electromagnetic emissions, they may not always result in visible lights. In fact, the signals may be too faint or too brief to be detected by the naked eye, leaving only a small fraction of these instances documented. Nonetheless, the potential for these emissions to act as a warning sign for impending earthquakes makes the phenomenon worth further study. Scientists are now working with advanced equipment, including satellite-based sensors and ground-based electromagnetic field monitoring systems, to detect these subtle emissions. One method being used is magnetotellurics, a technique that measures the Earth's natural electromagnetic fields at different frequencies. This approach has proven useful in studying the Earth's crust and upper mantle, but recent studies are also exploring its ability to detect seismic activity before it occurs. The idea is that these electromagnetic signals could be detected days or even weeks before a major seismic event. If electromagnetic radiation is indeed connected to seismic stress, These signals could serve as an early warning system, giving us time to prepare for an earthquake. In addition to electromagnetic radiation, there is also the theory that piezoelectricity, the generation of electric charge under mechanical stress, might be responsible for some of these strange light displays. When large faults or fractures in the Earth's crust experience pressure, the minerals that make up the rocks can produce electrical charges. For example, quartz, which is abundant in the Earth's crust, is known to have piezoelectric properties. As the Earth's crust is compressed or shifted during seismic activity, the piezoelectric effect could cause a buildup of electrical energy. This energy might be released in bursts, which could then ionize the surrounding air, creating the glowing effects that people have reported observing before an earthquake. One aspect of this theory that is particularly fascinating is the idea that these piezoelectric discharges might not always be visible to the naked eye. In some cases, the energy release may be so small or so brief that it remains undetected. However, in rare instances, the accumulated electrical energy might be enough to create visible light, either by ionizing the air or interacting with other atmospheric conditions, like high humidity or particular cloud formations. This would explain why people sometimes report seeing lights or flashes in the sky before an earthquake occurs, particularly when these events happen in areas known to have high levels of tectonic activity. Piezoelectricity in the Earth's crust is not just a theoretical concept. There is evidence suggesting that it may play a role in triggering certain types of earthquakes. Some studies have found that piezoelectric effects could potentially lower the friction between tectonic plates, causing them to slip more easily. In this sense, the electrical discharges generated by seismic stress might not only explain the lights people see before an earthquake but might also contribute to the event itself. This connection between piezoelectricity and seismic activity is still being explored, but it could offer an exciting new perspective on the causes of earthquakes and their potential warning signs. At the same time, it's important to consider that while these lights might be linked to the physical processes occurring within the Earth, they might also have a psychological component. Some experts argue that the appearance of strange lights could be an incidental byproduct of the intense emotional and psychological stress experienced by people in earthquake-prone areas. The anticipation of a major earthquake, combined with heightened alertness and anxiety, might cause individuals to perceive flashes of light or other visual anomalies in the sky that aren't physically related to seismic activity at all. In this way, the lights could be a psychological response to the subconscious awareness of seismic danger, rather than a direct result of seismic activity. Nonetheless, the fact that these lights have been recorded in multiple locations before significant earthquakes, and that they often exhibit characteristics associated with electromagnetic phenomena, means that they cannot be easily dismissed. Whether caused by piezoelectric discharges, electromagnetic radiation, or some combination of factors, these strange lights remain an intriguing subject of study for scientists. What's clear is that the search for an earthquake precursor, something that might give us a reliable signal of impending seismic activity, has led researchers down some unexpected paths, including the investigation of luminous phenomena in the sky. The hope is that by understanding these strange lights, we might one day unlock the ability to predict earthquakes with greater accuracy, saving countless lives in the process. To expand further on the potential link between strange lights and seismic activity, one must also consider the role of atmospheric pressure variations and how they may interact with electromagnetic phenomena. Tectonic stress and the shifting of massive fault lines can lead to changes in the atmospheric pressure, especially in regions close to fault zones. This phenomenon can cause pressure gradients to form, which may influence the movement of air masses and, in turn, affect how electromagnetic radiation behaves in the upper atmosphere. When an earthquake is imminent, the energy that builds up along tectonic plates creates not only seismic waves but also significant changes in the surrounding air pressure. These pressure changes could potentially enhance the ability of electromagnetic radiation to travel or ionize the atmosphere. The ionosphere, which is an electrically charged layer of the Earth's atmosphere, could be more sensitive to such changes, potentially triggering visible lights or electrical discharges in the sky. The scientific community has speculated that the disruption of this balance could be one of the reasons why luminous phenomena, often seen before earthquakes, are more pronounced during certain types of seismic events. Furthermore, atmospheric pressure fluctuations could contribute to the formation of what is known as quasi-static fields. These low-frequency electromagnetic fields, which are generated by changes in the atmosphere, could amplify the electromagnetic emissions that are already produced by seismic stress. In some cases, the quasi-static fields could act as a kind of amplifier for the electromagnetic radiation coming from the Earth's crust, making it more noticeable to observers. These fields might interact with the particles in the atmosphere, especially when they encounter ionized air or water vapor, which could lead to the formation of visible light displays. Another important aspect to consider in this context is the concept of piezoelectric phenomena in rocks. As mentioned before, piezoelectricity is the generation of electric charge under mechanical stress, and it occurs in various minerals and crystals present in the Earth's crust, such as quartz and calcite. However, the extent to which these minerals contribute to the formation of luminous phenomena is still being investigated. When tectonic stress causes these minerals to deform, they can produce an electric field strong enough to ionize the surrounding air. This ionization process can lead to the creation of visible lights, akin to what we see in phenomena like lightning. In the case of earthquakes, this release of energy could be more significant and more concentrated, which might explain why some observers report seeing brightly glowing or even pulsating lights in the sky before a quake. The behavior of the earthquake lights might also be tied to the frequency of seismic waves themselves. There is growing evidence to suggest that certain types of seismic waves, particularly P waves, primary waves, may be capable of interacting with the Earth's ionosphere. P waves, being the fastest seismic waves, travel through the Earth's interior before the more destructive secondary waves, S waves, arrive. In certain circumstances, the passage of these waves could generate enough electromagnetic disturbance to trigger visible electrical discharges in the atmosphere. This phenomenon has been observed in several instances where unusual lighting patterns coincided with the arrival of P waves in areas close to earthquake epicenters. As the P waves propagate, they could potentially cause atmospheric ionization, giving rise to visible light displays that serve as an eerie warning before the more violent shaking begins. One of the more fascinating possibilities is the potential connection between these strange lights and high-frequency radio waves. Some studies have suggested that the seismic stress in the Earth's crust can cause a disruption in the natural propagation of radio waves. These radio waves, which typically travel along the Earth's surface, could be refracted or reflected by seismic activity, especially in areas with active fault lines. This phenomenon might lead to unusual patterns of electromagnetic radiation that create visible effects in the atmosphere, such as the glowing lights seen in earthquake-prone regions. These high-frequency radio waves could also interact with satellites and communication systems, which is why reports of strange lights are sometimes accompanied by communication disruptions before major seismic events. Interestingly, the timing and location of these lights can offer clues about their origin. Earthquake lights are often observed in close proximity to fault lines and during specific seismic events, such as before a major earthquake or along a series of smaller quakes. This suggests that there is a direct connection between tectonic stress and the visible phenomena in the sky. By analyzing the specific characteristics of the lights, such as their color, intensity, and duration, scientists may be able to pinpoint certain fault zones that are more likely to produce these electromagnetic anomalies. This knowledge could aid in the development of early warning systems, providing a potential way to predict when an earthquake might strike, especially in regions where seismic activity is prevalent. Another possible cause of the strange lights observed before earthquakes could be related to the phenomenon of radon gas emissions and how they interact with the atmosphere. Radon is a naturally occurring radioactive gas that is produced by the decay of uranium and thorium in the Earth's crust. It is colorless, odorless, and tasteless, making it difficult to detect without specialized equipment. Radon is known to accumulate in confined spaces, such as basements, but it can also seep out into the atmosphere in higher concentrations in areas of seismic activity. When seismic events, such as earthquakes, occur, they can cause fractures and shifts in the Earth's crust. This seismic stress has the potential to release trapped radon gas from deep within the ground. In some cases, this sudden release of radon gas could create an ionized zone in the atmosphere, especially if the gas interacts with water vapor or other atmospheric particles. Radon gas, being radioactive, could ionize the surrounding air, creating a field of charged particles. This field could lead to the formation of visible lights or electrical discharges in the sky, similar to the phenomenon observed with earthquake lights. The ionization effect from radon gas could be amplified by the tectonic stresses that occur prior to an earthquake. As the fault lines move and shift, they may cause a greater release of radon, which would, in turn, heighten the ionization process in the atmosphere. This interaction could explain why some observers report seeing strange lights or glows near fault zones just before a major earthquake strikes. Additionally, the release of radon gas might also be tied to increased levels of electromagnetic activity, as the gas could influence the conductivity of the atmosphere, allowing electrical charges to build up more easily. Radon emissions could also potentially explain the pulsating or flickering nature of some earthquake-related lights. As radon is released in bursts due to seismic activity, the ionization of the air may not be constant, leading to fluctuating patterns of visible light. This might manifest as intermittent flashes or streaks of light that are characteristic of some earthquake light sightings. In some instances, the lights might appear to be tied to specific fault movements, suggesting a direct relationship between the release of radon and the electromagnetic phenomena in the atmosphere. Beyond just ionizing the air, radon might also be contributing to the creation of electrostatic charges that result in the atmospheric displays. Electrostatic discharge, commonly known as lightning, is caused when electric charges build up between different regions of the atmosphere. In areas where radon emissions are high, particularly in seismic hotspots, the concentration of charged particles could contribute to the buildup of such electrostatic charges. This could lead to phenomena similar to lightning or other electrical discharges seen in the sky, which may be misinterpreted as strange lights or auroras before an earthquake. Another intriguing aspect of radon emissions is their potential impact on barometric pressure. As radon gas escapes from the ground, it can create localized pockets of higher pressure in the atmosphere. These pockets of pressure might interact with other atmospheric conditions, causing shifts in the ionosphere or changes in the behavior of weather patterns. These changes could potentially lead to the creation of visible light displays or unusual atmospheric effects. Moreover, the combined effect of seismic activity and radon release might create the ideal conditions for the formation of unusual light phenomena, which are often observed before earthquakes. The timing of radon emissions and the subsequent electromagnetic effects could also be of great importance in understanding earthquake lights. While radon is a slow-releasing gas, its levels could increase suddenly in the days or hours leading up to an earthquake. This sudden increase in radon levels might correspond with the final stages of tectonic stress buildup, offering a possible explanation for why some earthquake lights are observed just before a quake. Additionally, the presence of radon in the atmosphere might be indicative of tectonic activity that is more likely to trigger these visual displays. In terms of scientific research, studies have been conducted to measure radon levels in regions prone to seismic activity. These studies have found that, in some areas, there is a noticeable spike in radon emissions prior to major earthquakes. This has prompted scientists to explore whether there is a direct correlation between these gas releases and the appearance of earthquake lights. However, the evidence remains inconclusive, as radon emissions can be influenced by a variety of other factors, such as weather conditions, geological characteristics, and the presence of nearby human activity. Despite this, the potential connection between radon emissions and strange lights is an area of active investigation. One of the main challenges in studying the link between radon and earthquake lights is the unpredictability of both phenomena. Radon levels can fluctuate due to a variety of natural factors, and the presence of strange lights is often sporadic, making it difficult to establish a consistent pattern. Additionally, radon is not the only possible cause of ionization in the atmosphere, and other factors, such as cosmic radiation or the aforementioned piezoelectric effects in minerals, may also contribute to the phenomenon. Nevertheless, the possibility that radon plays a role in the creation of earthquake lights is an intriguing avenue for further research. Delving deeper into the connection between radon emissions and seismic activity, there are additional layers to explore in understanding how the release of radon could potentially trigger these strange light phenomena. Radon gas is a noble gas, and as such, it has a relatively stable and inert chemical behavior. However, when it is released into the atmosphere in higher concentrations, it can interact with other elements and compounds, contributing to a range of physical effects. These interactions could be a crucial part of how radon might influence atmospheric conditions that lead to the strange lights observed before earthquakes. When radon is released from the Earth's crust due to seismic stress, it could be accompanied by an increase in other volatile gases that may be present in the same fault zone. For example, methane, carbon dioxide, or hydrogen sulfide could be released simultaneously. The combined presence of these gases, along with the radon, might increase the overall ionization in the atmosphere. When radon decays, it emits alpha particles, which can interact with nearby molecules in the air, knocking electrons loose and creating ions. This process could lead to the formation of plasma-like conditions, where charged particles are more easily able to move and build up in certain regions of the atmosphere. In areas of intense seismic activity, where the radon gas might accumulate in significant quantities, the ionization effect could be powerful enough to create small localized electrical fields. This ionization could potentially cause the formation of lightning-like discharges or glowing phenomena, as charged particles interact with the atmosphere. These phenomena would not be traditional lightning bolts but rather more subtle, atmospheric light displays that can flicker or pulse in intensity as the pressure and concentration of radon change. The visual appearance of these lights could be in the form of faint glows in the sky, halos, or even arcs that appear to emerge from specific fault zones just before a major earthquake. One important aspect to consider is the effect of moisture in the air. High humidity or changes in atmospheric pressure can play a crucial role in the visibility of ionization effects. The presence of water vapor in the air could contribute to the overall electrical properties of the atmosphere, potentially enhancing the visibility of the charged particles that are generated by radon. The moisture might create a more conducive environment for light phenomena, as water droplets could scatter light from ionized particles, making the light displays more noticeable to observers on the ground. Additionally, the ionized air might act as a conductor, allowing electrical discharges to propagate more easily, leading to the creation of electrical arcs or glows that are often linked to earthquake light events. Furthermore, the release of radon gas could influence the ionization of the ionosphere. The ionosphere, which is the layer of Earth's atmosphere that contains charged particles, plays a key role in the propagation of radio waves and other electromagnetic signals. During seismic activity, the release of radon and other gases could alter the ionosphere's properties, creating localized pockets of increased ion density. This could contribute to the creation of electromagnetic anomalies, which might manifest as strange lights in the sky, particularly near fault lines or areas with active seismic zones. These electromagnetic disturbances could trigger plasma-like discharges in the atmosphere that might resemble aurora borealis-type lights or flashes, adding to the complexity of the earthquake light phenomenon. In addition to the direct interaction of radon with the atmosphere, another aspect worth considering is the way that the release of gases like radon might affect the Earth's crust itself. In some instances, shifts in the Earth's tectonic plates can cause sudden fractures in underground rock formations, which might create micro-fissures or gaps that allow radon to escape. These fractures could be accompanied by an increase in electrical conductivity within the Earth's crust itself. The fracturing of minerals such as quartz under tectonic stress can result in piezoelectric effects, where mechanical stress is converted into electrical charge. This process could potentially amplify the ionization effects of radon, making it more likely that electrical discharges would occur in the atmosphere above. The combination of radon emissions, piezoelectric effects, and atmospheric ionization could significantly increase the likelihood of visible lights or electrical phenomena before earthquakes. Moreover, seismic activity might create conditions that cause radon to be released in pulses, not in a continuous flow. These pulses could be tied to the final stages of tectonic shifts when the Earth's crust is under maximum stress. This release pattern might explain why the strange lights observed in the sky before earthquakes are often described as intermittent, fluctuating, or pulsing. As radon is released in bursts due to seismic stress, these pulses of gas could lead to variable levels of ionization in the air. The fluctuating concentrations of radon and other gases might create an unstable atmospheric environment, where electrical charges build up in some areas, leading to brief and localized discharges of light. Additionally, while radon itself is colorless, it can interact with the various minerals and gases in the ground and the atmosphere. When radon decays into its byproducts, these particles can also contribute to the overall atmospheric changes. Radon's radioactive decay produces elements like bismuth, polonium, and lead, which are also ionizing. These particles could further exacerbate the ionization process, potentially causing more vivid or erratic light phenomena. As these particles move through the atmosphere, they could generate small electrical sparks or flares that are perceived as glowing lights, halos, or flashes near fault lines. The depth at which radon accumulates is another factor that might influence its potential to cause atmospheric light effects. Radon concentrations vary depending on geological conditions, and areas with deeper tectonic layers may see more significant bursts of radon emissions. In contrast, regions with more shallow fault zones might experience less dramatic radon releases, potentially explaining why some earthquakes are preceded by light displays while others are not. In regions with significant tectonic pressure or deep underground reservoirs of radon, the release of gas could be accompanied by more powerful ionization effects, leading to more pronounced visible light phenomena. Given that radon is often undetectable by the naked eye and requires specialized equipment to measure its presence in the atmosphere, it is difficult to directly link specific instances of earthquake lights to radon emissions without thorough scientific investigation. However, researchers are continuing to explore the connection between gas emissions, atmospheric ionization, and seismic activity, especially in fault-prone regions where earthquake lights have been observed in the past. The possibility that radon, a naturally occurring gas, could contribute to the phenomenon of earthquake lights adds another layer of complexity to the study of pre-earthquake phenomena and could offer a new direction for understanding the mysterious visual effects that have puzzled scientists for years. The connection between radon emissions, unusual light phenomena, and seismic activity, if further explored and proven, could have transformative effects on our ability to understand and predict natural disasters, especially earthquakes. One of the most pressing challenges in the field of seismology is the inability to predict earthquakes with high precision and accuracy. While various methods are used to monitor and study seismic activity, such as measuring tremors, monitoring fault lines, and analyzing historical data, the unpredictable nature of earthquakes means that warning systems, for now, remain limited. The idea that unusual light phenomena, potentially tied to radon emissions or ionization of particles in the atmosphere, could serve as an early warning system would be a game-changer in this regard. If the lights observed in some earthquake-prone regions are indeed linked to radon gas released from the Earth's crust before seismic events, understanding the mechanism behind these phenomena could be the key to a predictive model. Radon, as a naturally occurring radioactive gas, emanates from the decay of uranium found in the Earth's crust. It typically moves upward through the soil, sometimes entering homes, but in the context of seismic activity, it could be released in larger quantities as tectonic stress fractures the rock beneath the surface. This could create an ionized environment, especially in areas with significant tectonic movement, which may result in unusual atmospheric phenomena, like the earthquake lights seen prior to a tremor. These lights, observed as flashes, glowing clouds, or even arcs, could be a visible manifestation of the shifting energies beneath the surface. The key question would be whether the appearance of these lights follows a predictable pattern, correlating with seismic events in such a way that it can serve as an actionable warning. If proven to be true, this phenomenon would add a new dimension to earthquake prediction, providing people with critical moments, if not hours, to prepare for what is to come. For example, In densely populated regions, even a few minutes of notice could save thousands of lives by giving authorities time to initiate evacuations, alert people, and secure critical infrastructure. The integration of this light phenomenon into existing seismic monitoring systems could offer a multi-layered approach to earthquake prediction. It would not replace current methods but could act as an early signal that complements other data like ground tremors, shifting fault lines, and gas emissions. Combining these elements would allow for a more holistic understanding of seismic activity and provide a more comprehensive warning system. On a broader scientific level, researching the link between these unusual lights and seismic activity could open new avenues in understanding how the Earth's crust interacts with the atmosphere. This could lead to deeper insights into the processes that cause earthquakes, such as the movements of tectonic plates and the buildup of stress within fault zones. It could also uncover more about the role of gases like radon in influencing atmospheric conditions. If ionized particles or other gases are responsible for these light displays, scientists could develop new techniques to monitor the levels and concentration of these substances. In doing so, they could potentially detect early warning signs of seismic shifts far earlier than current ground-based methods allow. Moreover, this phenomenon could contribute to an entirely new field of atmospheric and ionospheric science. If radon or other gases are affecting the ionosphere and producing visible phenomena, studying these interactions could reveal patterns in Earth's electromagnetic field and provide valuable data on the forces at play during seismic events. This might lead to technological advancements that allow for better real-time monitoring of the Earth's atmosphere and crust, enabling predictive systems to be established not just for earthquakes, but other natural events like volcanic eruptions and tsunamis. The long-term implications could even extend beyond Earth's boundaries. If such mechanisms are further explored, they could provide insights into planetary sciences and the study of other celestial bodies. It may be that similar phenomena could be observed on other planets or moons, particularly those that experience tectonic shifts or other forms of seismic-like activity. In essence, the potential relationship between radon gas, atmospheric ionization, and earthquake lights could unlock a wealth of new understanding and technological advancements. By shedding light on these phenomena and verifying their connection to seismic events, we would not only advance earthquake preparedness and safety protocols but also contribute to a broader understanding of Earth's dynamic systems and the way they interact with the atmosphere. The discovery could revolutionize how we perceive and respond to natural disasters, equipping humanity with more tools to protect lives and mitigate the impacts of these devastating events. Another possibility for the strange lights observed before earthquakes could be tied to a theoretical effect involving the Earth's magnetic field. When large seismic events occur, they may create disturbances in the planet's magnetic field that could potentially cause ionization in the atmosphere. This ionization process might trigger bursts of light, which could explain the glowing phenomena often reported in the lead-up to or during seismic activity. Seismic activity, particularly when a large fault line is involved, can create shifts in the Earth's magnetic properties. These shifts could, in theory, create localized electromagnetic fields in specific regions. As the Earth's magnetic field fluctuates due to the movement of the tectonic plates, these disturbances could interact with the ionosphere and cause it to release energy in the form of visible light. One possible mechanism for this might be the sudden displacement of charged particles in the Earth's crust as tectonic plates grind against each other. These displacements could send waves of energy into the surrounding rock layers, which might be strong enough to induce electromagnetic currents. These currents could then interact with atmospheric gases, possibly leading to the ionization of air particles, creating a brief flash of light. In this scenario, the glowing lights would be less of a direct physical reaction like lightning, but more of an atmospheric phenomenon caused by shifts in electromagnetic energy, amplified by seismic activity. The lights would likely appear as flashes or glows, often described as appearing in the sky before or around the time of major earthquakes, possibly reflecting the energy pulsing through the atmosphere as a result of tectonic shifts. While this is a speculative theory, it aligns with a growing body of research suggesting that seismic activity can influence the Earth's magnetic field. Given that the planet's magnetic field is essential in protecting the atmosphere, Any disruption in it could have unexpected consequences, including unusual atmospheric phenomena. These magnetic disturbances might not only cause shifts in the physical landscape but could also potentially create the right conditions for lights to appear, either from direct ionization or from the release of trapped electrical energy in the atmosphere. In such a case, the lights could be a form of energy release from deep within the Earth, traveling outward as seismic waves disturb the Earth's magnetic field. The unpredictable nature of this phenomenon might explain why it has been difficult to fully study and understand the correlation between earthquakes and the strange lights witnessed in the sky. Building upon the theory of electromagnetic disturbances in the Earth's magnetic field, the relationship between seismic activity and unusual lights in the sky could be further elaborated through a deeper exploration of the interactions between seismic waves and the ionosphere. The Earth's ionosphere, a layer of charged particles above the surface, plays a critical role in the propagation of electromagnetic waves. When large seismic events occur, they have the potential to send shockwaves through the Earth's crust, which can disturb the magnetic field surrounding the planet. These disruptions may ripple outward, triggering various atmospheric responses, including the creation of light phenomena. One possibility is that as seismic waves travel through the Earth's crust, they induce the movement of charged particles in the rocks. This could lead to what's known as seismic electric fields, a theoretical concept that suggests seismic activity might generate small electrical currents within the Earth itself. These currents could then travel upwards toward the ionosphere, where they interact with the charged particles already present. As these particles encounter ionized air molecules, they could produce visible flashes of light. This mechanism would rely on the conversion of mechanical energy from seismic vibrations into electrical energy, which then gets released as photons when it interacts with the atmosphere. Additionally, seismic waves traveling through the Earth might also influence the local atmospheric pressure and temperature, creating disturbances that could interact with nearby clouds and atmospheric gases. The sudden changes in air pressure and temperature could contribute to the ionization of these gases, leading to visible glowing phenomena. While this process might resemble phenomena like auroras or lightning, the key difference is that these lights would likely be localized, only appearing in specific areas where seismic disturbances are most intense. Another intriguing factor is the role of fault lines and the associated tectonic activity. Fault zones are often characterized by complex geological structures, with layers of rock that are under immense stress before an earthquake occurs. This stress might lead to the release of charged particles from minerals within the Earth's crust. When these particles are expelled into the atmosphere, they could ionize the surrounding air, producing a glow. The exact mechanism by which this occurs is not fully understood, but it's hypothesized that large earthquakes could create an electric potential between layers of rock in the atmosphere, much like how a capacitor stores and releases energy. Furthermore, in certain cases, the magnitude and depth of the earthquake could impact the strength and duration of the electromagnetic effects. Deeper earthquakes, in particular, may generate more substantial shifts in the Earth's magnetic field. The greater the disturbance in the magnetic field, the more significant the potential for light generation in the upper atmosphere. These lights could range from faint glows to more intense bursts of light, depending on the scale of the seismic activity and the amount of energy released. It is also worth considering how certain environmental factors could influence the visibility and nature of these lights. For example, the atmospheric conditions in a specific region, such as humidity, cloud cover, or the presence of particular gas concentrations, might amplify or dampen the effect of seismic-induced lights. In regions with more frequent tectonic activity, the likelihood of these lights occurring might increase, especially if the geological conditions are favorable for such electromagnetic disturbances. The observed relationship between strange lights and earthquakes could also be part of a larger, yet to be understood phenomenon. These lights may not only be a result of seismic activity, but could also be connected to the Earth's deeper energy systems. This would suggest that as tectonic plates shift, they might release stored electromagnetic energy that travels outward, creating disturbances in the atmosphere. These disturbances might cause light to be emitted, but the exact conditions for this energy release could be rare, leading to the intermittent and unpredictable nature of the phenomenon. As the scientific community continues to explore this connection, it may lead to further advancements in understanding how seismic events interact with the Earth's magnetic field, ionosphere, and atmospheric layers. Such insights could open the door to potential methods of predicting seismic events based on electromagnetic anomalies, or even lead to new technologies for monitoring the Earth's magnetic and atmospheric behaviors. However, as of now, this remains an area of active speculation and research, with more studies needed to clarify the exact mechanisms that produce these fascinating and mysterious lights before earthquakes. Shifting focus to another potential cause, let's consider the possibility of gas emissions and their relationship to seismic activity. This theory proposes that certain gases, which are released from the Earth's crust during tectonic shifts, could play a significant role in generating unusual light phenomena. The idea is rooted in the fact that seismic activity can cause underground pressure changes, which in turn release gases like methane, radon, and other volatile compounds from deep within the Earth. These gases, once released, may interact with the atmosphere in ways that result in visible lights. When seismic waves travel through the Earth's crust, they can disturb pockets of gas trapped in the rock layers. These gases, which are often under high pressure, could escape through fractures created by tectonic movement. As these gases make their way to the surface, they may interact with the atmosphere in a variety of ways, potentially causing ionization and the emission of light. For example, methane, a common gas associated with seismic activity, could mix with atmospheric oxygen and undergo a process known as combustion or chemical oxidation, which might produce light. Beyond methane, radon gas is another significant player. Radon is a naturally occurring radioactive gas that emanates from the decay of uranium in rocks and soil. When seismic events cause fractures or shifts in the Earth's crust, radon gas can be released into the atmosphere. This gas is radioactive and can ionize the surrounding air molecules. As radon interacts with the oxygen and nitrogen in the atmosphere, it may result in ionization that could produce a faint glow in the sky. This phenomenon, known as earthquake lights in some parts of the world, has been theorized to occur due to the presence of radon in specific seismic areas. The release of these gases into the atmosphere could be particularly pronounced in certain geographic regions, such as areas with high tectonic activity or locations near volcanic sites. Volcanic regions, for instance, are known to release large quantities of gases during seismic events. These emissions may not only contribute to visible light, but could also lead to the formation of other atmospheric disturbances like auroras or lightning-like effects. This would depend on the concentration of gases and their chemical properties when mixed with the surrounding environment. In terms of ionization, when these gases are released into the air, they can create localized pockets of charged particles, similar to the processes seen in lightning or auroras. These particles could accumulate at higher altitudes, where they might interact with other atmospheric elements, creating flashes or glowing phenomena. Additionally, the presence of such gases could cause the atmosphere to become more conductive, making it easier for natural electrical phenomena to occur, such as small-scale lightning discharges that could be visible as brief flashes in the sky. Furthermore, the geographical location of the seismic activity can influence how these gas emissions impact the visibility of such lights. In areas with more stable atmospheric conditions, the release of gases might have little visible effect, while in regions with unstable weather patterns, such as those prone to thunderstorms or high winds, the light phenomenon may be more pronounced. This interplay between gas emissions, atmospheric conditions, and seismic activity could provide a unique set of conditions that triggers these phenomena. Also, the scale of the seismic event plays a role in the extent of the gas release. Minor tremors may not release enough gas to create noticeable lights, whereas larger, more powerful earthquakes or volcanic eruptions could release vast amounts of gases, increasing the likelihood of observable light displays. In some cases, the chemical reactions that take place during these gas releases may even be amplified by the energy from the seismic waves themselves, leading to more intense and frequent light shows. Research into the specific gases involved, as well as their behavior in the atmosphere during seismic events, is still in its early stages. However, It's clear that gas emissions could contribute to the unusual lights observed in some earthquake-prone areas. As we step back and examine the potential connections between the strange lights observed before seismic events and the forces that drive these natural occurrences, we find ourselves at a crossroads of mystery and discovery. The intriguing phenomenon of lights in the sky, often seen before or during earthquakes, has puzzled many for centuries, leaving us with more questions than answers. Despite the abundance of theories, ranging from well-established scientific principles to more speculative and unconventional ideas, the full extent of the relationship between these lights and seismic activity remains elusive. However, this does not detract from their significance. If anything, it magnifies the need for continued inquiry and exploration. The ongoing study of unusual lights in connection with earthquakes suggests that the Earth is much more than a static entity. It is a living, breathing organism, continuously changing and responding to both visible and invisible forces that shape its very core. Earthquakes, volcanic eruptions, and the subtle movements of tectonic plates may not only be triggers for seismic waves that we feel beneath our feet, but may also stir reactions within the atmosphere above, producing phenomena that we can observe in the sky. Whether these lights are caused by electrical charges, ionization, or even chemical reactions in the atmosphere, we are reminded that our planet operates in a far more complex manner than we fully understand. The interaction between the Earth's surface and its atmospheric layers is still a mystery that scientists are striving to unlock. In exploring the many possible explanations for these lights, whether they are linked to gas emissions, piezoelectric effects, or even the electromagnetic influence of the Earth's magnetic field, we begin to uncover a complex web of connections that is far from fully mapped. As we dig deeper into the phenomenon, we are faced with the stark reality that the forces governing these occurrences are often invisible to the naked eye. They exist in the spaces between scientific knowledge and our everyday experiences, where the boundaries of what we know are stretched and tested. Our inability to fully comprehend these events only adds to their allure, making them all the more significant as we attempt to bridge the gap between natural phenomena and the scientific understanding we have thus far developed. Furthermore, the human experience of witnessing these lights often provides a unique window into the way natural events affect our perception of the world around us. As seismic events are often unpredictable, the idea that a warning might appear in the form of strange lights above us suggests a possibility of forewarning or a signal that we are, in some way, connected to the Earth's movements in a way that we have yet to fully grasp. Whether these lights are precursors, or simply coincidental atmospheric phenomena, they remind us of our vulnerability and our continuous quest for knowledge about the planet we call home. One of the most profound implications of this mysterious link is the broader impact on our understanding of Earth's interconnected systems. These lights could very well be the tip of an iceberg, offering a glimpse into an area of study that could revolutionize how we perceive seismic activity and natural disasters. If we were able to determine a reliable pattern or connection between these phenomena, it could lead to a deeper understanding of how we might predict earthquakes, or, at the very least, better prepare for them. This could have massive consequences for how we approach disaster preparedness, urban planning, and even the very way we understand Earth's behavior over time. Still, as we explore these connections, we must be cautious not to let speculation cloud our judgment. We live in an age where new technologies and research methods allow us to gather and analyze data at unprecedented levels, which means we are more equipped than ever to explore these complex relationships. However, it is also important to remember that the natural world is filled with nuance and unpredictability. Earthquakes and seismic events are driven by forces that remain beyond our control, and the mystery of these lights may continue to elude us despite our best efforts. What we can do, however, is continue to ask questions, to explore new theories, and to remain open to the possibility that there are aspects of our planet that we have yet to discover. The strange lights that appear before earthquakes are a fascinating reminder of just how much we have yet to learn about the world around us. While they may be elusive and mysterious, they also represent a new frontier in the study of natural phenomena, one that may lead to answers we have been seeking for centuries. As we move forward, it is essential that we continue to investigate the connections between these lights and seismic events. We need to continue expanding our research efforts and fostering collaboration between scientists, researchers, and communities that are affected by these natural occurrences. By pooling resources and knowledge, we stand a better chance of unraveling the mystery behind the lights in the sky, which could ultimately lead to a deeper understanding of our planet's behavior. In the grand scheme of things, the connection between lights and earthquakes represents just one of many pieces in the puzzle of how the Earth works. The fact that this puzzle is incomplete is a reminder of how much there is yet to learn about the forces that shape our world. Perhaps in time, new discoveries will lead us closer to the truth, and we will unlock the full story behind these phenomena. Until then, we must continue to seek knowledge with curiosity and perseverance, knowing that each piece of the puzzle we uncover brings us one step closer to understanding the mysteries of our planet. If you found this exploration of the mysterious lights and their potential connection to seismic activity as fascinating as we did, don't forget to hit that like button. Your support helps us continue diving deep into the unknown and uncovering the hidden forces shaping our world. Make sure to subscribe and ring the bell so you never miss an update as we continue unraveling the mysteries of Earth's powerful forces. Stay curious, stay informed, and thanks for joining us on this journey.